That is a plan. So today, so far we have discussed few of the logical things: quantum software, quantum gates, quantum state representation. What is qubit? So ultimately, all these things are very much logical level, right? But today we will be looking into more of the hardware-oriented aspects of quantum computation, primarily a few of the quantum technologies, and also we will try to analyze the viability or a kind of all those technologies with respect to some specific applications that we will try to at least understand that how it works or what is the criteria, how to choose that which technology to use depending on the exact business requirement. So at least try to understand it based on the current state of the art and everything. So also we will be covering a few of the drivers, okay, or the primary factors that are driving all these kind of categories of technologies and their current usage. So in order to understand quantum technology and their key elements, first thing is what you need to do is you need to understand a few of the a bit more hardware oriented terms, right? So what are they? We'll try to analyze it not only theoretically, but most of the things today will be theoretical, but at least I will try to analyze it in a very realistic way, that what you should be keeping in mind. That is the target. I hope the screen is visible. I hope the screen is visible. Yeah. So first one is a qubit type. That what type of qubits I might need. So different implementations are there for the qubit representation or the way it is built up. Firstly, it is superconducting qubits. There is a trapped ion architecture. Approx cost of 8 qubit quantum computer. Okay, I do not exactly know what will be the cost. Also, that depends on I think very the specific company from which or from where you want to get that device. It also depends on the error rates and all those things, I guess. So I don't have any real kind of figures to give you for that. I think there is a lot of factors that you need to consider over here in order to understand that what is the total price, the error contained within the qubit or the quantum computers that they're offering. That is a thing. How much of usage you want. Okay, because generally the quantum computers are like sold in terms of not the entire computer, but depending on the some of the computation that you want to do. That is in terms of the usage. So 5% of that one or say 10% of that one, depending on that 1% of that one. That is one thing. Second is for how much of the duration you want to have that computer, access to that computer. That is another one. So there are a lot of some factors that you need to consider. So depending on that, there are different implementations, and these implementations are also called the machine descriptions at physical level. So these are called physical machine descriptions. Okay. So what are they? Like few of them are superconducting qubits, trapped ion architecture, photonic qubit, like few of you are telling that screen is not visible. No, we are on the first slide where it is understanding quantum technologies and some of their key elements. Okay, so this was the first slide. That is the introductory slide, then followed by this thing. So we are on the first slide. Okay. Nothing is visible. Is that the case? Q201 screen is only visible, but it should not be.
Your screen is visible, ma'am. There are no issues. Maybe there are some issues with participants' internet or connectivity. So we can see your second slides now, understanding quantum technologies and their key elements. It's visible.
Yes.
Right. Thank you, ma'am. Please continue.
Okay, sure. Please rejoin. because I think many of you are facing this. Please rejoin. Okay. So they are like superconducting qubits, trapped ion, linear and non-linear photonics, topological qubits. Likewise, there are certain technologies. So first factor is a qubit time. Second factor is the coherence time. Coherence time means the time for that, or the duration which specifies that how long the quantum information is retained within a quantum state just before decoherence. So this is a kind of a coherence time. Okay, that also is another factor in order to understand or choose that which of the technology you want to have. Because depending on its in architectural level, what are the changes, what are the elements, what are the physical setup kind of thing that are being done. So based on that, the coherence time of the qubits can also differ. Okay. Now gate fidelity. Gate fidelity means how accurately some quantum gates are operating on respective qubits. So how accurate their operations are. That is defined by gate fidelity. Scalability means it is used to evaluate the feasibility of increasing qubit numbers without losing the performance. That is scalability, definitely. So that is without losing performance is very theoretical level, but actually it determines that there should not be any significant, because right now if you increase your qubit number, definitely the performance will degrade. But the thing is that it should be taking place in an optimum level. That is the thing that you have to keep in mind. So if there is a linearity in that, so you will tell that okay. But if anything drastic changes happen, then you will call that okay. So this particular type of technology is not really scalable. Okay. Then error rates. Different technologies have varying noise because they are built up with the help of different hardware. And different physics are behind that. So they are having a different noise and error susceptibility levels. Okay. Error susceptibility means that how much that particular system is susceptible to the error. That is how error prone that system is and how noisy that system is. These are the two things that you have to consider. Quantum volume, it is a holistic measure of quantum computational power. You can think it of just like number of qubit is one of the metric and quantum volume is another metric, where it is like a combination of, in very easy words, it's kind of a combination of quantum bit count or qubit count as well as the error content in it. So kind of a balance in between two. So based on that, considering both the factors, we tried to measure that how good or how say resilient a quantum computer is. For example, if I say that I have a quantum computer of say 10 qubits, and if someone else says that I have a quantum computer of 20 qubits, these two statements versus if I say that I have a quantum volume of 64, someone else will tell me that I have a quantum volume of 128. Now, what is the difference? Means in the latter case, it means that quantum volume 64 is associated with a certain number of qubit count and a certain number of error content. Whereas I am claiming that if it is superior, if it is quantum volume of 128, then definitely it is more powerful or more better to have than a qubit 64. That is kind of an assumption. Okay, so quantum volume, you can think it of like a metric, just like qubits. It is another metric, but it is not really that much of a tangible metric. It's a quality metric. You can think it of like that. Okay. Operational temperature. Some qubits require near absolute zero cooling, and while others work at room temperature, which is a big research area right now. They want, because only in few countries quantum computer, just like Canada or somewhere, you can think it of that the environment is most suitable kind of that. But in countries like ours, it is very difficult. So or for tropical countries, so it is very much required in order to find some kind of a technology which is kind of that can work at room temperature or near room temperature. If that can be done, that is a breakthrough that can happen. Then it's a control mechanisms. Different quantum systems use microwaves, lasers, and optical methods for manipulation, you know that. Connectivity is another factor, which is a kind of a key elements for qubit technologies or quantum technology, that how the different qubits within that particular system are interacting, how they are interconnected, because their interconnection will determine a lot of other stuffs, how their strengths are, how they are interfering each other, how much, whether it's a like loosely coupled system or a tightly coupled system. Now, depending on that, coupling or strength of coupling, there will be further consequences. There are chances of decoherence that can be also understood depending on the interconnection or interconnectivity between, say, the qubits. Just for example, say for example, I have a linear connectivity of all the qubits. It's just like an array, kind of an arrangement. Okay. Versus I have, say for example, a two-dimensional kind of a qubit arrangement. Now, of course, you can understand that, say, a linear arrangement is not really very advantageous than the 2D arrangement. Why? Because, say, for example, one qubit is in position 1 and the 10th qubit is in position 2, to have certain interaction between them. So, ideally, there are other ways to mitigate it, but even if we try for it, ideally, because they are so far from each other, then definitely the decoherence chances will be very, very high, and like mitigating this particular disadvantage will take more number of some costly investments into the picture, which we generally do with respect to certain kind of a swap gates. So we try to incorporate some swap gates so that wherever there is a like of this kind of non-linearity in between two interacting qubits, so that it can be linear, so that they are just like adjacent or somewhere connected with each other. We try to establish that kind of connection. Now, if you imagine, say I have 1 to 10 and 1 and 10 are somewhere wants to enter, like say communicate or do something. So how many in this particular arrangement, how many swap gates I might require? So first I need to swap, I can swap either 1 or 10. Let me assume I'm swapping 10. So 9 and 10 first swapping. Then again with 10, I have to now swap 8 and 10. Now again 10 and 7. Likewise, it needs to, just like a like insertion sort or something. So it needs to come just beside 1 or say at position 3, so that at least their strength remains, their amplitude remains, and whatever is the coherence time, that also can be properly justified or that can be established. So connectivity of qubits is a very important factor to consider. 10th one is the integration with classical systems. So it says that how well your quantum devices can work with the existing classical infrastructure. Why it is very much important? It's purely important with respect to the business requirements. We all know that migrating fully from certain system to another system is not that easy. So kind of some compatibility, if that exists, it will be very, or at least the transition to from an old technology to a new technology will be a bit smooth. So that is another kind of an aspect that you should be considering for a quantum technology, just in order to migrate from the existing classical to the upcoming quantum. Okay. Now, comparison between the quantum technologies. Okay. So, few features I have identified right here, and few of the like 5 quantum technologies in here: superconducting qubit, trapped ion, neutral ion, photonic one, and topological one. Yet we have not seen that what is the respective technology, how it behaves like, but just before doing ground at least some of the factors that you can keep in mind. Okay. So qubit type, the qubit type for superconducting qubit was Josephson junctions that is used. What is Josephson junction? We will tell or talk about it just after a few minutes. Then trapped ion, it uses a kind of ionized atoms as its qubits. Then neutral atom itself uses neutral atom. So that is the qubit here. And photonic qubit uses kind of a polarized photons. Okay. And topological qubits is basically we call it. Okay. Second property is gate operations, where how on that particular qubit, how some gate will operate on that qubit. So we do these operations with respect to a certain kind of a physical things, like microwave pulses for superconducting, laser-based technology for trapped ion, optical tweezers, which is a kind of a very focused laser beam, you can think it of like that, for neutral atom, optical interference for photonic ones, and braiding operations for this thing like topological, where we braiding means kind of an exchange between the like two states in order to represent a certain information. Okay, then coherence time, I just explained what is coherence time. And depending on different qubit technology, they have different kind of coherence time. Error rate, which is moderate, low, high, and expected very low. Topological is just like beginning. It just had started its journey. So for maximum of these cases, for topological, you will not see like significant growth there because of the very new area and very like minimum number of R&D experiments done on it. So I am sharing the screen. I am on the slide with the title Comparison of Quantum Technologies. I don't think there should be any problem with it. Okay. 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 So scalability for superconducting, it is a bit challenging. For trapped ion, it's moderate. Likewise, you can check it. Okay. Quantum volume, connectivity, gate fidelity, how accurately the gates are operating on particular quantum states. Then it's basically the speed that they have, whether like speed of operation or kind of that, how much like fast a quantum technology is with respect to other in terms of the quantum operations being performed with the help of those technologies. And cooling requirements, because these require a very like absolute near zero temperature kind of thing. But for few technologies, it is also doable in room temperature. Measurement mechanism, what technology we use for measurement? So it's a microwave detection for superconducting, fluorescence for trapped ion, for photonic, it's a photo detector, all these things. Okay, error correction feasibility. There is a high requirement of error correction feasibility for superconducting qubits. For trapped ion, the like feasibility is moderate, and here it is also moderate for this thing. Okay, for the neutral atom. For photonic, it is difficult, and topological, it is expected to be very high. Okay, material requirement, again the same thing, fabrication complexity, commercial availability. So on availability basis, you can see, because that is why we always say that we use the superconducting qubit architecture. Remaining all technologies right now are in niche level in terms of they are not really fully mature in terms of their R&D. So mostly we'll be seeing like IBM, Google, Rigetti, D-Wave, all these things. Despite D-Wave's technology is based on the annealing model or adiabatic model of computing, and all the others are based on the brick model of computing. It is typically, you can see that kind of all of them uses this superconducting qubits. Okay. Now, and also there is just one like particular company called IonQ, which uses ion trap or trapped ion qubit architecture. So that is also commercially right now available. So mostly these two technologies are like something that you can use, and they're available as well. State of development, you can see, so it's leading. One is superconducting one, quite matured one is trapped ion. Rapidly advancing is the neutral atom. Photonic is in early stage, and topological is yet in the experimental stage. Error mitigation method. So quantum error correction happens or is needed for superconducting qubit. What is a quantum error correction? It's like a very big thing to discuss. Just in short, let me tell you, quantum error correction incorporates that for every like erroneous qubit, I should be putting some backup qubit kind of that. Okay, so that whenever it's kind of, so one player is playing, now say 4 players are just covering up that particular player. So if anything happens, any mishap happens during the game with that player, so any one of the remaining 4 players should be able to back him up. Someone will be doing something, someone will actually manage something, someone will maybe push it, kind of that. I will talk about it. Topological, just wait. Okay, so this is a concept of a quantum error correction, and this QEC or quantum error correction brings up the concept of a physical qubit and a logical qubit. So here, that is why I said that one logical qubit needs to be error corrected and all. So one physical qubit needs 1,000 number of logical qubits in order to do the similar kind of a computation. So that is the limit of the error content. But this information is of 2022. This is 2025. I'm not sure about that what exactly is that particular relationship or that ratio is currently. But even 2 years back, this was the story. Okay, and even if now I don't believe that it's very significantly something good that you can see. But we should not be losing hope here, because we already have shifted to think that what is a certain kind of a like fault tolerant one. How can I make my logic itself error corrected? That is the concept of error correction. How I can make my qubit error corrected so that I need not to bother about the amount of error and something. So that is first step. Second step is, once I do certain error correction, so how I can use very improved error correction technique so that it is kind of a maximization of performance and minimization of number of quantum operations or number of quantum bits or qubits required for error correction. So likewise, maximization, minimization, a lot of such factors are there for quantum error correction that we can think it of. Dynamic decoupling, that is used for trapped ion. And for this neutral atom, it is basically some form of quantum error correction. For photonic qubit, it's kind of an adaptive error correction, where we do or perform error correction based on the real-time feedback on the qubit performance. So it's kind of an adaptive network that we use in order to perform error correction. And for topological qubit, we perform topological encoding. So topology means a certain kind of a structure, at least this one or that we call as a topology. Even in our network system or computer network, we call it a mesh topology, ring topology, bus topology. So at least it is a particular kind of a arrangement of which determines a specific information. So few nodes, depending on in what topology they are in, their resilience, their cost, their interconnectivity, all those things changes. And all of them are associated with a certain amount of information. All those topologies. Okay. Cost of implementation, you can check it. Energy consumption also. Nothing to explain here. Quantum network suitability. It's another point. Suitability in NISQ computing. This is something I want to emphasize a bit more. NISQ stands for Noisy Intermediate Scale Quantum. This is the current era where we are in. Exactly this time we are in NISQ era, where we believe that our systems are intermediate at intermediate scale. That is, neither they are in a very like low level, low scale, or neither they are not there in a very position where they are like fully commercially available or that kind of a viability they have. Okay, so their scale is kind of an intermediate scale, and also the systems are very much noisy. So it's not true intermediate scale quantum system or quantum era. So for NISQ era, we mostly think of the variational quantum algorithm approach, VQA, not VQE. Okay. So variational algorithm means we will be having a certain sort of a quantum circuit. We will be giving some input. We will be getting some output. Now, depending on the output, there will be certain change into the next iteration's parameter setting, so that I can fine tune the performance of the quantum circuit depending on the parameters, the new parameters. Likewise, okay, so it's kind of a reinforcement learning type of concept basically, but it happens through the change of parameters of every time through the variational way. Depending on how is the deviation, based on the deviation from the ideal and the actual, we try to modulate our next iteration in. Okay. And also the NISQ computing mostly rely on the hybrid model for the classical quantum one. Of course, you can understand that only with this much of a noisy system, only with quantum, some good results are very difficult to be shown. I will not say that it is impossible theoretically, but it is very difficult to be shown. Okay, so we have to think of certain strategic way out for that. Got it? So we have to think of a certain hybrid kind of a solution, where very less amount of part will be there, for which we will rely on the quantum one, and bulk of the very kind of a streamline operations we will be performing in the classical ones only. And through some variational approach, we will, from based on the classical, we will feed into the quantum one, and that result we will again feed into the classical, check how much is the deviation, how good it is, how bad it is, and we will change our intermediate quantum circuit, kind of that. So suitability of NISQ is very high for superconducting and trapped ion. That is why they are right now commercially available. I hope now you are getting it. And potential for fault tolerant quantum computing is moderate for superconducting one. It's trapped ion, it's very high. It has a high potential. Neutral atom also, it has very high potential. For photonic, it is low. So where I'm telling it is low means that the factors to determine that whether it's fault tolerant or not, that is not applicable in case of a photonic ones. Okay, and for topological, it's high. All that results for topological is based on a theoretical, the so far done theoretical researches. Physical size of the qubit system, it is large for superconducting, large for the trapped ion, small for the neutral atom, like an array based. It's a fiber based kind of structure for a photonic qubit, and it is for like unknown yet for a topological. Speed of entanglement generation, that is fast with the Josephson junction and superconducting. Integration with classical, it is very strong for the hybrid quantum classical architecture and the NISQ thing. Just I mentioned this. Best for optimization problems, yes. Best for quantum simulations. So as of now, just consider first two columns, superconducting and trapped ion. So both are yes. Best for cryptographic applications, it is moderate. Okay, it's very high for photonic qubits because we use the photon polarizations for all the quantum cryptography and quantum communication related applications. So photonic qubit has the primary application in the fields of cryptography and communication and like quantum network in all these kind of fields. Okay, for satellite communications. So for similar kind of areas, photonic qubits are most widely used. And best for AI and machine learning, so moderately it's high for both the superconducting as well as the trapped one. So now not all quantum computers are built the same. Different companies use different ways to build it. So here you can see that what are the main players here. So superconducting are used by IBM, Google, Rigetti, these companies. IonQ, Quantinum, which was also, I think it was some Honeywell Quantum Solutions. It kind of, right now Quantinum has taken it, or I guess so. So Honeywell Quantum Solutions, right now it's used by Quantinum. So they use the trapped ion one. Neutral atom is Qubera and Pascal. Psi Quantum, Xanadu, that is based on photonic qubits. Topological qubits is recently launched by Microsoft in their one of the projects. It is just had launched. So topological qubits are being explored by Microsoft, and this kind of nitrogen vacancy center qubits or diamond center qubits is also there, which is yet to be adopted by some company. So now a bit more detailed. Again, these are theoretical, very much theoretical. So bit more detail about the superconducting qubits and all these kind of the technologies that we have seen. So think of superconducting qubits as a very tiny quantum circuit, that work at super low temperatures. Okay, so how it works is, so definitely it is not like something that can be covered in one slide, but for quantum computing, unless you are like able to work in a lab where these kind of quantum technologies or some are being that kind of experiments are taking place. So it will be, to my belief, it will be theoretical for you as well. For that, what I thought is to highlight the most important points so that you can at least have a brief idea of what are these quantum technologies. Okay. So superconducting one is based on a Josephson junction. It's a kind of a superconductor followed by an insulator followed by a superconductor in order to create the quantum state. We are not going into very detail of it. That is not required, I guess. Qubits are controlled using microwave pulses that manipulate the quantum states, and here temperature requirement is near absolute zero. Is unmuted. Please try to mute yourself. Okay. So advantage is fast quantum gates. Okay, it's very fast. Most commercially mature quantum hardware. Challenges is the short coherence time. So that is why a lot of these optimizations are required, and very smart qubit routing techniques, qubit communication techniques are coming into picture or coming into research, and expensive cryogenic cooling is required. Okay. So trapped ion qubit is quantum at atomic level, says. So imagine using individual atoms as your qubits. So this is what trapped ion quantum computing does. How it works is it uses a kind of a charged atomic ions trapped into electromagnetic fields. Qubits are stored in hyperfine energy levels. Okay. And what is a hyperfine energy level? Hyperfine energy levels are energy levels that can arise due to the interaction between the nuclear and the electric field. So that kind of a energy level is known as a hyperfine energy level. Okay, and they are controlled using a precisely tuned laser pulses. Advantage is extremely high coherence time, high gate fidelity, which is best among all the qubit types. Challenges is laser control is very complex here, and quantum gates is also very slow. Okay. And INQ was the first one who built this trapped ion quantum computer. Okay. So neutral atom qubits. So this is kind of soft wizard beams are used, or they are used on neutral atom to make it behave like a quantum bits. And atoms can be rearranged in real time, just like a moving chess pieces. And entanglement is achieved with the help of a grid bar excitation. So these excitation means it's a very kind of it uses a highly excited atomic states for quantum computing and like quantum simulation for those things. So it's a kind of a very highly excited atomic state. So with the help of that, we can actually establish entanglement for neutral atom hardware architecture. They are scalable. That is the biggest advantage. No need for cryogenic cooling. It is very, very advantageous. Okay. Challenges is precision laser alignment is difficult. So noise level will be that will actually increase, and there will be a lots of attenuation into the system, and still it is in a early research phase. And QERA uses this kind of setup. Photonic qubits, where we use basically the photon polarizations or light itself in order and make that thing behave like our qubits. So how it works is it uses a single photons itself as qubits. Quantum gates are performed using these kind of optical elements like beam splitter, phase shifter, and interferometers. Interferometer means to detect the rotation and the phase shift with high precision. Okay. And beam splitter means basically where you are actually breaking the light into multiple components of it, depending on the optical barrier that you are putting in front of light. Okay. So that is kind of a beam splitter, and phase shifter is what you know, like you just change the phase of the light beam that is being passed through the filter. So there can be different type of filter for photonic, like there can be depending on different bases, you can say. So one can be that can break your light into, say, or that can let your light pass through the horizontal and the vertical basis, which is just say the kind of a y-axis, kind of that. And also it can be your 45-degree and 135-degree basis. So just like a cross or just like a plus. A plus means a horizontal vertical basis, or a cross or multiplication sign. Say for example, for a plus 45-degree and minus 45-degree, which is nothing but 135-degree. You can think it of in that way. So all those things are coming into picture, and different bases and photon passing through them are used to represent different set of quantum information. So that is another like area of study that starts from this thing. Advantage is no decoherence. Photons do not interact with their environment. No concept of decoherence there. Works at room temperature, best for quantum communication and quantum cryptography, all those areas. Challenges is very hard to implement 2-qubit gates. Photon loss is a big problem. But Xanadu computer is based on the photonic architecture. And also like photonic architecture is based on two different types. So one is based on the linear photonic architecture, and another one is based on the non-linearity of the photonic architecture. So they are called photonic, just like electronics. Electronics is the behavior of electrons. Photonics is the behavior of photons. Okay. So those qubits which are like inspired by the behavior of photons at the linear level, they are called linear photonics. And similarly, the same thing for non-linear photonics as well. Okay. So yes. Now next one is the silicon qubits. So we build using the silicon processors. That's the goal of silicon spin qubits. It uses Is it now okay? Okay. And screen is visible? Screen is also visible? Okay. 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 So silicon qubits, I was just explaining. I guess all of you were able to hear till the photonic qubits. So now is the next thing is the silicon qubits. Let me again explain it. So silicon qubits are based on kind of we want an interface between the classical hardware and a quantum hardware, where we want to define a kind of a silicon spin qubits which follow the silicon quantum dot architecture, where a single electrons are trapped in a silicon quantum dots, and that based on that we represent a valid information, valid quantum information or no. That kind of a presence or absence of information we represent with that kind of a single electron trapping. And this is advantageous because it is compatible with the classical metal oxide, like complementary classical CMOS, which is a complementary metal oxide semiconductor. And it is also very long term. It has a long term scalability potential. Challenges is it is still in an experimental phase, requires Microsoft Well, now again just reconnected. Okay, thank you, thank you. Let me again, please. Let me share. Yes. So I was just explaining the topological qubits, which is kind of, first of all, the topological qubit is kind of a ultimate fault tolerant setup where we are believing that ideally we will be having some automatic scalar, automatic error free or scalable uh, uh, like quantum technology or qubit architecture, where we use a kind of fermions which is thought of like also it's called Majorana fermions. So we believe that these fermions are kind of a hypothetical particles which are assumed to be stable in the fault tolerant quantum era. Okay, so we are believing in that particular thing. So that is why it is inherently fault tolerant. We do not, or we will not be requiring any quantum error correction, or very less amount of quantum error correction is required, and could enable scalable quantum computing as well. But it is still theoretical, no large scale demonstrations yet. And Microsoft is betting big on these topological qubits with its new project. You can also have a more of the information regarding these topological qubits. It is their new project called Station Q. So it is a kind of a qubit that naturally can protect itself from errors, and they actually exchange information based on their inherent topology. But that topology defines a particular quantum information, which whenever they are interacting, they will exchange. So because of that automatic exchange of information based on their state, we call that these are very much of an error free. But the real demonstration is not yet done, so it's still pending. So now the thing is the strategic approach to selecting a quantum technology. Okay, now the theoretical stuffs we have seen already. Now we will be just discussing a little bit on this thing, that what are the things that you should be keeping in your mind before choosing or before deciding that which is your ideal technology. And also with the technology, there are other factors also. So those things will also come into picture. First of all, I'll go to each one of them individually. Okay, so this is just an analysis now of the quantum technologies with respect to different real scenarios. Let us do that as well, instead of only the theory. So why does the right quantum technology matter? Because not all quantum technologies are built the same way, and different methods suit different business needs. So scalability, error tolerance, gate speed or quantum gate speed, speed of operation, their connectivity, all these things define the success of a quantum application. Okay. And a wrong quantum technology choice can mean inefficient quantum computation, a wasted investment, and a delay in the practical results as well. Now, there are certain things or certain questions that someone should be asking before choosing their respective technology. What is the first question? That is, what problem are we solving? That is in what domain we are into. Are we doing it in optimization or cryptography or machine learning, chemistry, finance, etc.? So what is our respective industry? That we have to first define. For example, if I want to use cryptography, I will be using this thing. What is the thing? That is the photonic architecture. But if I want to use, say, for example, say some logistics use case or optimization, we might use the superconducting qubits. Next question that we should be asking is, how much scalability do we need? That is, whether we need to devise prototype level, or we want a really scalable thing. So how much is the real requirement of the scalability that we want? So 10 qubits or 1000 qubits, or say 1 million qubits. That is next thing that you should be questioning yourself. Third one is how much error or noise we can tolerate. Can we right now focus on some of the a noisy intermediate scale one, where we know it will be noisy? So that means our system has to be reliable based on only speed and immediate availability, but it will not be fully reliable in terms of the error containment within that measurement outcome. It might be erroneous. So we have to keep it in mind. Or we also can think of a certain sort of a classical post-processing or post-error correction in classical level, if not quantum level, in order to deal with it. Or we might incorporate both the things. Because our circuits are noisy, we will be using a quantum error correction to correct some of the qubits or correct some of the outcome. Then we will be also using a further some of the classical error correction in communication. Okay, those things we will be using. So that is the thing. That is how much precision you want your system to be in. Whether you want it to be a high precision or some approximate answers are also acceptable. A very easy example from computer network I can give it to you, like the transport layer in our OSI protocol stack. We have two protocols, right? The very well-known two protocols are TCP and UDP. If you just can recall that wherever we need a certain kind of a more reliable architecture, we did not really bother about how much costly our system is. But we focused or emphasized on some other factors. What were those factors? That is, there should be very, or say, no to minimum number of packet drop. We should all be getting valid acknowledgement. If we do not get, third point is, if we do not get an acknowledgement, then our system should be adaptive enough, okay, to control the packet size or to control the packet number of packets that is being sent. So all these things you are keeping in your mind because your primary focus was the precision. But for UDP, the header size itself, everything was very small. Only a little checksum was there and the source and the destination IP address, all these things are there. But all the header information where you can do all this error correction, all these things are not included for UDP. Because UDP was based on a best effort delivery, where we just want it immediately, we want it to be fast, but it can contain certain form of a error inbuilt. So where time was our primary focus, we choose UDP, and where reliability, all these things were our primary focus, we choose TCP. If cost is our primary focus, we will be using UDP. If we can go for there is a relaxation that on the usage or the cost, then we can go for TCP. So it is ultimately our business requirement that we first need to jot down. Okay, so there is nothing kind of an ideal or perfect. That depends on perfect or imperfect, depends on our specific business requirements, right? The next one is, what infrastructure constraints exist? That is, do I have the option to support the system or the environment to be compatible with the cryogenic cooling? Can I support laser system? Do I have that much of a hardware resources available to set up a photonic network? Now, what you have depending on the underlying infrastructure that you require, what you can support based on the infrastructure requirements, first you need to finalize, then only you can choose for what is your suitable technology. Next one is, how soon we need the results to come. Whether we want it to be near term or whether you want a future-proof technology investment. That is, we're investing for future. Right now, we have the time to develop the prototype, and we will be doing finally some commercial traction will come once it is fully kind of mature. So based on all these questions, now a quantum developer must guide businesses based on these constraints, ensuring the most viable solution to be chosen. So matching business use cases to the required quantum technology is, first you need to identify the business challenge now. See, these are something that is with respect to the hardware part. Now for a particular technology, there is another thing also that is coming, which is the logical things, right? So that kind of an operational feasibility also you have to think of, not only the technical feasibility. What is the first thing? That is, you have to identify the business challenge. First, is the problem really computationally hard for your classical systems? For example, I have given you just to find the minimum item in an array. So for example, only this thing. Now for this particular problem, it is already very easy problem. It is doable in classical systems. So we will not be choosing at all any easy problem for our business real demonstration because it is useless. or we have to really bring that much of a like advantage, just like Grover. Initially it was n, right now it's root over of n. Okay, we have to show it. But if we cannot show it, that will be a loss. So it's better to choose a certain sort of computationally hard or NP hard problem that in classical is really very challenging to do. Second is computationally hard means your NP hard or NP complete, that things out of the complexity classes. Second is, does the company require quantum speed up for specific task? That is, what is the requirement of the company? Where it wants certain improvement to be taking place. Whether it wants only a demonstration, they really do not care about the quantum, speed up. They just want something to be quantum, then you will go for the whatever is right now available. Or they want that what will happen if we have a like full-fledged prototype designed with us and we can actually run it in the FTQC era or fault tolerant era. That is another kind of a requirement. If it is like a comparison between a classical and a quantum that they want to perform with respect to say traffic optimization, traffic flow optimization, then that is another kind of a requirement. So you have to very specifically for your specific task identify that what kind of requirement from quantum you have. You want only the infiltration into quantum, that is some part will be done in quantum, speed up ho na ho, does not matter, or you want some real speed up to be taking place. Both are okay based on the requirements. Because there might be certain cases where because of the immaturity of the quantum system that right now exists, you can never show quantum speed up. Does it mean then there you should not be using or should not be thinking for any quantum solution? That is also not true. This is what I am trying to actually point out. Third one is, will quantum computing outperform your classical alternatives in this domain? So meanwhile, I just want to do a like quality check. Is the voice and my screen fully visible and audible? Just give a thumbs up. Okay, thanks for confirming. Thanks. Okay, so the third question was, will quantum computing outperform classical alternatives in this domain? Okay, so if all the things are true, it is yes, then quantum definitely is a right choice for you to explore. Again, to only explore. You do not know what exactly will happen at the end, but we have to do the experiments. Second step is define your quantum hardware requirements. Now, based on here, will some subject matter expert will come into picture. Okay, till what like step one, a simple consultant can work, no issue. But here you need your deep expertise into where you need to devise your quantum algorithm. That quantum algorithm needs to be converted to a quantum circuit. That quantum circuit you have to like just fully open. You have to open that quantum circuit in terms of like decoding that quantum circuit in terms of what is the gate fidelity. You have to check how many quantum gates, what are the redundant gates. If there is any redundancy, you have to solve it. All these things at logical level, first you have to complete. Okay, now you have to think on that what will be in the real essence, in the real implementation, while we will be doing it on the physical hardware, what can be the few of the challenges that exist with the quantum circuit. There you have to think of the connectivity of qubits. So maybe some routing, some communication, how to reduce the communication overhead between qubits, how to make the all the like decoherence less, all those things you have to think. Second is, does this business need a near-term or a cloud accessible quantum computer? So if it is yes, near term, then definitely you cannot use topological ones or neutral atom. You have to go for superconducting, or say for if it is cryptography related, we'll have to go for some photonic one. Third is, does a company lack infrastructure for cryogenic? If so, then go for the photonic or silicon or diamond nitrogen vacancy kind of architecture. And this diamond NV, nitrogen vacancy, basically here, a defects in diamond is actually also used to encode some information for quantum computing. That is the diamond NV architecture. NV stands for nitrogen vacancy. Okay, so step 3, once you have done or like defined or done all the hardware requirement checking, next step is you have to match the business use case, right? Business use case to the right technology. Now you know what your technologies are, what different quantum technologies offer, I guess. From so far, whatever we have seen, you have seen their features, you have understood the business requirements, you made a like technical bridging between them, that what does it mean. Everything logical statement has a like technical image or kind of a footprint as well. So once you have everything ready, now you have to choose that whether it's the right technology or not. Here again comes the concept of vendors, how to choose who is the right vendor for you for that particular technology. Okay, then the like cost, reliability, you have to go for the proof of concepts that whatever they're claiming that they have, whether they really have it or not. All those viability you have to physically or say through certain kind of validation reports you have to check and find out. I think you are understanding a 360 now of quantum. So we started with a physics, quantum physics. What was superposition? We also have seen so much of maths yesterday. Right now, it's so much of a business oriented or the real hardware oriented stuff and the bridging basically, that how the theory and the real world, how to map between these two like areas. What theoretically might be very, very promising, might not really be perfect for the practical applications, and vice versa, and also vice versa. Whatever you can see, say practically, you cannot do it on really go for a theoretical research for quantum. So there are a lot of things here. Okay. So business use cases is, say, for example, you have logistic optimization where supply chain, vehicle routing, warehouse management, all these things are there. So base quantum technology will be superconducting qubits, neutral atom qubits, all these things. And why? Because the fast gate speeds and good optimization algorithms that the superconducting one and these ones actually, what to say, they provide. Yeah. So it's QAOA or quantum approximate optimization algorithm. It will not be, because it's very much, it's nothing is yet done. क्या करें उसका तो मतलब it's only to map the real business use cases with the real available quantum technologies. अगर real कुछ होता तो शायद होता, but right now maybe something will happen after 2 years or maybe after 1 year or 5 year, whatever it is, depending on what the project queue it goes like, or some of the startups might also come up with some solution to topological for the real implementation level. Okay. So financial risk analysis is Monte Carlo simulation, portfolio optimization. For this, for everyone is thinking of some exam, I guess, today's exam. So superconducting qubits, trapped ions, and why is they are on topological? Yes, both are same thing. That is the fermions. Topological qubit is the architecture, and the fermions used are say Majorana, it's called. So that is the fermions kind, or say the particles for topological qubits that is used. And why is the and financial risk analysis? Why these two things? Because speed and entanglement benefit the probabilistic simulations. Okay. Drug discovery, trapped ion and superconducting, because high fidelity qubits required for quantum chemistry, that is precision is very important. We have to opt for a minimum error. Cyber security and cryptography, photonic qubits and silicon qubits, because photonic QKD is very secure. Quantum key distribution, we will see this in our next 3 lectures when we will cover the cryptography and communication, what is QKD and all. But definitely it's free from no cloning theorem, and no eavesdropping is possible. So it's very secure, QKD, photonic QKD. And silicon may enable quantum resistant encryption. And AI and machine learning acceleration, superconducting, photonic both, because quantum enhanced neural networks need rapid gate execution, which is offered by your superconducting. And quantum networking and secure communication, again, photonic qubits and diamond NV centers. And why? Because the photonic qubits travel long distances, enabling secure communication. Okay. So future proofing your quantum investment is basically a roadmap for business is for near term, it has to be some sort of a small scale quantum adoption. So go for the cloud solutions that is offered. Okay. like Amazon Web Service or your kind of IBM Cloud for quantum, Google Quantum, all these things, where they provide a certain kind of a cloud platform. And use cases are, and of course, the technologies are superconducting and trapped ion, which is most commercially viable because we need it right now, near term. Okay. Use cases are optimization, chemistry, and financial modeling. Midterm is where you will be having some scalable solution, but it will be erroneous. So quantum error and all these things are prediction. Do not really say that okay, this is 2036 and I till date do not have a fault tolerant one. So these are just the predictive kind of what they are doing depending on the past results and all. Okay, so they're just predicting the timeline to be like this. So scalable quantum, but why we can rely on this? Because all the tech giants are claiming the same thing. When everyone is like behind something, then we generally believe that, okay, so that is a reliable source of information that we can rely on. So quantum error correction improves for a scalable one, and 1,000+ qubit system might emerge. It's a large scale trapped neutral atom and silicon qubits. In these areas, we can see some sort of advancements. AI and quantum computing hybrid models become mainstream, maybe. Okay, so hybrid solutions, more of these solutions will be developed, more libraries and a lot of other stuffs will be more matured in terms of hybrid one. Long term is what we can see beyond 2035, where it will be fully fault tolerant. We do not need much of the error correction because it's already every qubit will be fault tolerant itself. So 1 million+ qubit systems operational with very low error rate. That level of scalability you have to have. Quantum powered AI, secure quantum internet, pharma breakthrough, all these things will become reality. Large scale adoption in finance, logistics, defense, and climate modeling, that also will take place. And this long term era is when basically all your crypto systems will be broken. That is a definite thing that also I can promise. Because Shor's, if at least some of these things are true, then Shor's quantum algorithm, which was to break the RSA and ECC, all these kind of classical cryptography, they will be definitely broken. Now I can give you why. I can give you why. Why? Because is I will explain it for cryptography, but just for the sake of completeness for this topic, there is a thing called you harvest now or store now decrypt letter. That is, right now they will be storing it. Once this setup will be available, they will be using it to apply the brute force in lightning speed, and they will be able to break the crypto system. So that is why it's very threatening. Classical cryptography is the biggest threat due to quantum. Okay. So quantum cryptography may be a solution to that, may not be a solution, but where we should be like more focusing is our things should be very, very much free from any kind of a threat that quantum can offer or provide, say, in a negative way. And quantum speedups in NISQ and beyond, can NISQ surplus exascale classical hardware running? Really, can it do it? It is possible. Quantum advantage in near term is possible, but definitely there is no guaranteed. Hybrid algorithms like QA, OA, and VQE, they can be tested. Near term algorithm should be designed with noise resilience in mind. कि कुछ classically or quantumly we have to do some sort of fine tuning so that it becomes automatically noise resilient. Quantum dynamics of highly entangled system is especially hard to simulate and is therefore an especially promising arena of quantum advantage. And experimentation with quantum test bed may hasten the progress and inspire new algorithms. NISQ is not enough. The goal for near-term quantum platforms should be to pave the way for bigger payoffs using future devices. Definitely. So NISQ is not, of course, enough. But what right now we are using the NISQ ones, trying to mold our quantum systems in that way. But definitely, we are aiming for the FTQC era. And lower quantum gate error rates will lower the overhead cost of quantum error correction and extend the reach of quantum algorithms which do not need a error correction. A truly transformative quantum computing technology may need to be fault tolerant and so may still be far off. And we do not know for sure how long it will take, but the progress towards fault tolerant quantum computers must continue to be a high priority for quantum technology. What is the implication of what? What is the implication of what? I think implication of a lot of things it can be. I missed. Oh, sorry. It's related to me, please. Sorry. Okay. I can stop. Uh, this is just a few things just to give us marge between today's class and tomorrow's class. Engineer, how about the job market for a quantum engineer other than in research? Job market? No, it is not at all a stupid question. It's a very relevant question. So basically, it is so where exactly you want to get into, that's your choice. Job market in terms of salary remuneration, if you say, then research is the always the like biggest area where you can jump into. If you want some other kind of work, because there are some verticals of it as well, other than the fully this thing. So fully research or core research, I do not know. I do not know about the quantum dot cellular automata, but there was a paper. I was just once going through it. I found not to be very interesting for me, so I skipped it. Please, I'm keeping it for your research. Do your research, Dipti. Yes, could explain what? Okay. Uh, uh, Inside insulator. That is not really, the topological, are they right now available for commercial use? That is the thing. That is what I want to also know. I do not have such information yet that they can be like used. Maybe because no scalable such no use news we have yet got based on the scalability or how reliable the solution is like looking like. So maybe those things are there. Data storage means no storage kind of thing is here. I'm just telling is how to manipulate the information. So how to create the like superposition. Maybe for certain cases you will be just throwing some optical situations. That was the thing. Maybe some laser pulses. So different like elements will behave through certain operation as qubit. Now those qubits on maybe whenever we say logically say that a quantum gate is applied on that qubit, that may be something that is we are talking in a logical way, but physically maybe that again takes place because of certain say interferences into it. Okay, some like photonic interference or some other kind of a physical factors which is affecting it. I will be discussing on quantum error correcting code, but definitely maybe not in this level, this much of a very, for whatever is a new research, but the fundamental level I will be covering. So just wait for the next class. We will be covering. Because as you can see, I just tried to give us margin between the error correction, error terms. So errors in classical communication followed by some quantum communication. So few of the, maybe definitely few of the quantum error correcting code we will be discussing. Okay. Yes, adding parity is conventional. What do you mean by million rows? What do you mean by million of rows for Grover? So Grover is very simple thing. If it is an unstructured data with of n elements, then it require n number of states. N number of state means log n base 2 number of quantum bits will be required, or qubit will be required to build the Grover circuit, and it can solve the problem in root n of number of time. So it's clear. That is it. And also there is one extension that is um, um, I will be. Definitely, I will be. I'll put some time where further research areas we will be discussing. But that will probably happen on 12th. That is a plan. I will do few areas of research. Explicitly also I will try to mention in multiple domains, maybe. Or one or two or three domains I will pick up, and there I will, where I have some knowledge. Of course, quantum is so big. I do not have any knowledge on quantum sensing, a very minimum knowledge, which is almost negligible, but I have some knowledge for quantum cryptography, communication, information science, quantum information science, quantum algorithms. So, a little knowledge on quantum machine learning. So, this will be the areas where I will definitely try to guide you with what can be the future research areas. Okay. Yes. So, it's 3:22. I guess we can stop now today. You have your exam. I will be definitely. PQC is the one that I'm also right now doing for my research work. Already in the earlier industries also, I worked on that PQC, so I will be explaining it. Considering array as a key element for search means 10 lakh rows considering array. It's 10 lakh, 1 million means 10 lakh rows considering array as a key element for search. A Grover search. Row mean like one row of 1 million elements, right? This is what you are asking, I guess. So row has any significance here? You are asking something else. Yes, let me know what you are asking. Quantum computational fluid dynamics. Not have much of the idea. Only I know that it is used for like some modeling, and a few of the industries like aerospace and all. There it has some application. Honestly, only that much of knowledge I have for computational fluid dynamics and QCFT. Primary key we consider for database search. Huh. Okay. So primary key is also some item, right? That you want to search. Are you asking that Grover automatically from a now let me rephrase your question. So are you asking that if you have a relational database, that is what I am understanding that you are asking. If you have a relational database of few columns, okay, say for example a small table, say A, B, C, D, and that has certain data, if it is able to determine that which is your primary key or a set of keys, this is what you are asking, right? I guess. No, Grover cannot tell that. How? That is a different, completely different logic. It was like it has equivalence with the linear search algorithm. It has only the, I mean, definitely you can think it of like some of the parts you will be doing classically. Some of the part, I also do not know how to do that. So, but if you can think of certain areas where quantum amplitude amplification, you can think of that, okay, there is a specific way you have identified that way that okay, so every time this particular element or the primary key element has a certain feature except the kind of a functional dependency that is there, we'll also assume some more things are there. So Grover is best simple thing. It is there is an array, it will search an element. But for primary key there is a lot of concepts, right? You have to take you have to find the closure of that key, that is whether all the other elements are covering into it or not. Now, if you can encode this logic somewhere in the middle, maybe a QAA, you can put it as a component, then maybe this is doable. But directly, there is no sort of correlation or dependency between the Grover and the functional key, or say functional dependency or the primary key finding. Absolutely no relation. Yes. Okay. So it's 3:25. I also have another engagement from 3:30.